As we continue to consider ways to prepare ketones and aldehydes, our next approach is starting from acids. We've seen Grignard reagents and organolithium species, and we know that they are very strong nucleophiles. Well, organolithium species in particular are so very strong that they can react with a compound that actually has a negative charge. So even though we have a negative, this carbon is still partial plus. An organolithium species is a strong enough nucleophile to be able to share electrons with this carbon. So the R group will take its electrons and share them with this carbon, pushing these electrons up onto the oxygen. And so that gives us as an intermediate this compound, which is a dianion. Now, as part of the aqueous acid workup, both of these oxygens are going to be protonated, which gives a hydrate. So where we have two alcohols both connected to the same carbon, that is called a hydrate. This also is not isolated because this will react further. It will lose water to give this ketone. So a carboxylate can be treated with an organolithium species, and the net result is a ketone, which has this piece from the original carboxylate and this piece from the organolithium. If we're starting with a carboxylic acid, one option is that we can treat it with lithium hydroxide or sodium hydroxide or something just to generate the carboxylate, and then we can react it with an organolithium to give the dianion, followed by the hydrate, followed by the ketone. Another possibility is that we start with the carboxylic acid and we just use two equivalents of the organolithium species. And so one equivalent is going to first act as a base and grab off that proton, but our second equivalent then is going to act as a nucleophile and add to this carbon. So we see here that the reaction of a carboxylate plus an organolithium, this is a source of ketones. We have seen examples of esters being converted to alcohols. Well, can esters be converted to aldehydes? Let's take a look. If we have methyl benzoate, for example, if we were to treat this with sodium borohydride, remember that we get no reaction. So sodium borohydride is not strong enough. If instead we use lithium aluminum hydride, so a stronger hydride reducing agent, this is going to reduce the ester, but unfortunately it reduces it all the way down to the alcohol. And we're also going to get some methanol. So using lithium aluminum hydride in an ester, that doesn't help us to get aldehydes or ketones. Sodium borohydride isn't strong enough to reduce. Lithium aluminum hydride is kind of too strong. So dibol presents a nice alternative. So dibol is diisobutyl aluminum hydride. So we have aluminum with a hydrogen, and then this is connected to two isobutyl groups. So isobutyl, 1, 2, 3, 4 carbons, and there's a methyl branch. So we have diisobutyl aluminum hydride. Reduction with the diisobutyl aluminum hydride, and this is usually kept very cold, this will give us an aldehyde. So the ester is not reduced all the way down to the alcohol, it stops at the aldehyde. In other words, this is a great way to make aldehydes. So how does this work? We have our ester and we have our diisobutyl aluminum hydride. And so this is a source of H-, and so the H- is going to act as a nucleophile and share its electrons with the carbon, pushing these electrons up onto the oxygen, and that's going to form a complex with the dibol species, but it stops here. And another equivalent of dibol doesn't add. This species is stable until hydrolysis occurs. So when hydrolysis occurs, you can think about these electrons coming back here to reform the double bond, kicking out the OR as a leaving group, giving the aldehyde. So this is the hydride that came from the diisobutyl aluminum hydride, and this is the original part of the ester. And here's another example. We have an ethyl ester diball at minus 78 degrees Celsius, followed by an aqueous workup, is going to convert this ester to an aldehyde. As we consider other ways to prepare ketones and aldehydes, what about reduction of a carboxylic acid? Well, if we use lithium aluminum hydride followed by water, this will reduce the carboxylic acid, but unfortunately it reduces it all the way down to the alcohol, so that doesn't help us to make an aldehyde. Instead of an acid, what if we started with an acid chloride? If an acid chloride is treated with lithium aluminum hydride followed by water, again, a reduction will occur, but again, we end up with the alcohol. So that doesn't work. But an acid chloride can be reduced to an aldehyde, not using lithium aluminum hydride, but instead using a milder reducing agent. In particular, one that's very effective is called lithium tri-T-butoxy aluminum hydride. We have the aluminum with a hydrogen and 3 T-butoxy groups. That makes this a negative, and so then we have lithium as the counter ion. So here's this big, huge reagent. What we need to remember is that overall what this does is convert an acid chloride to an aldehyde, where this hydrogen is from the lithium tri-T-butoxy aluminum hydride. So let's look at a complete example. Here we're actually starting out with a carboxylic acid, but carboxylic acids can easily be converted to acid chlorides by treatment with thionyl chloride. And then the acid chloride can be treated with the T-butoxy aluminum hydride, and that is going to replace the chlorine with the hydride, giving us an aldehyde. So we see that acid chlorides provide another source of aldehydes. Now we have another reaction with acid chlorides, and if we treat these with a Grignard reagent, this is going to behave similarly to what we've seen with esters. So the Grignard serves as a source of a nucleophilic R group. So this is going to share its electrons with the carbonyl carbon, pushing these electrons up, and then those electrons will come back down, kick out the chloride, and we get a ketone intermediate. But then a second equivalent of Grignard can add, pushing up these electrons, giving us the alkoxide, and then on aqueous acid workup, we get the alcohol, a tertiary alcohol, where 2 equivalents of the Grignard have added. Now, if we were to use an organolithium instead of a Grignard, the same thing is going to happen. We get 2 additions leading to the tertiary alcohol rather than a ketone. But as an alternative, there's another species that's kind of related to the organolithiums, but it also includes copper. So this is a lithium dialkyl cuprate, also called a Gilman reagent. Now, a lithium dialkyl cuprate, we can kind of think of it like a mild nucleophile. It actually proceeds by a different mechanism, but the net result is it acts like a mild nucleophile. So we can imagine that this is going to add, kick these electrons up, they're going to come back down, kick out the chlorine, and we end up with the ketone, and it stops there. So for example, if we have benzoyl chloride and we treat this with lithium diethyl cuprate, this will give us ethyl phenyl ketone. So this piece came from the acid chloride, and this piece came from the cuprate. Now, where does the cuprate come from? So if we have an organolithium species and we treat that with copper iodide, that leads to the formation of a lithium dialkyl cuprate. But where do we get the organolithium from? Remember, if we were to use 2Rx plus, well, actually 4 lithium, that is going to give us 2 organolithiums plus 2 equivalents of lithium halide salt. We don't really care about that. The important thing is that from an organohalide, we can make an organolithium, and then we can make a lithium dialkyl cuprate. So for example, if we take 1-chlorobutane and we treat it first with lithium and then with copper iodide, we are going to make this lithium dibutyl cuprate. And then if we react the cuprate with an acid chloride, this is the product we will get, where this piece comes from the acid chloride and this piece was added via the cuprate. So we see that acid chlorides treated with cuprates, this is a source of ketones. Is it possible to prepare ketones or aldehydes from nitriles? Well, if we take a Grignard reagent and we react it with a nitrile, we can prepare a ketone. So what's going on? Keep in mind that for a nitrile or a cyanide, this carbon has a partial plus, and so a Grignard reagent wants to share electrons with that carbon. So we can see that here, the R group is going to attack the carbon, pushing these electrons onto the nitrogen, giving this C double bond N is called an imine. And so here we have a magnesium salt of the imine, where this was the original part of the nitrile, and this was added by the Grignard reagent. Now on aqueous acid workup, some of the acid is first of all going to break up this complex, and so that gives the imine rather than the salt of the imine, but then it goes further to convert the imine to the ketone. So what was the imine carbon becomes the carbonyl carbon. So imines can be hydrolyzed to ketones. This is the reverse of imine formation, which we're going to look at a little bit later. But what we see here is that this is another convenient way to make ketones. So for a specific example, we could react benzonitrile with phenylmagnesium bromide. So this is going to add to this carbon, pushing these electrons onto the nitrogen, giving us this imine salt. And then with hydrolysis, first this imine salt is going to be converted to an imine with an NH, and then the imine will be converted to this ketone. So nitriles can be a source of ketones. Can we access ketones or aldehydes in other ways from nitriles? What if we carried out a reduction? If we have a nitrile such as benzonitrile and we treat it with lithium aluminum hydride, this is going to give us a primary amine. So yes, it reduces a nitrile, but it reduces it all the way to the amine, so that doesn't help us. On the other hand, if we reduce it with dibol, diisobutyl aluminum hydride, this is going to give us an aldehyde, where the nitrile carbon becomes the carbonyl carbon. So what's going on? We have our nitrile, and with dibol, this is a source of hydride. So the hydride is going to add to the carbon, push these electrons onto the nitrogen, and we get this imine salt with the aluminum. On aqueous acid workup, this imine salt will be converted to the imine and then hydrolyzed to the carbonyl containing compound, which in this case is going to be an aldehyde. The nitrile becomes the aldehyde, where the nitrile carbon becomes the carbonyl carbon. The hydrogen of the aldehyde, this came from the dibol. And then the nitrogen part of the nitrile, that is going to be an ammonium byproduct. So to look at a specific example, if we have hex 4-ene-O nitrile, so carbon 1, 2, 3, 4 ene, 5, 6, so it's hex. So this can be reduced with dibol, where this carbon is converted to this aldehyde. And so we have 1, 2, 3, 4, 5, 6, right? So our nitrile carbon becomes the aldehyde carbon. On the previous slide, we saw that nitriles could be converted to ketones. Now we see that nitriles can also be converted to aldehydes.